All right, everyone, welcome back to the Synthesis Workshop. Today we have a very special episode that one's been in the work for, well, I guess a while now. I guess almost 2 months now. We've been really thinking about this. Title of this new series, the jury is still out on whether we want to keep the name, but I think overall it'll stay at, how can we make this? And in this series, we have two graduate students. Today we're joined by, I'm joined by Noah, and we're also joined by guest, quote-unquote judge, Professor Jeremy May, who's an associate professor, or a full professor here at the University of Houston in total synthesis. Noah as well, a graduate Ph.D. candidate in Seth Herzon's lab at Yale University. And today's series is, I think the purpose of it is to kind of get some insight into how one would do a total synthesis. I think there's thousands of lectures and seminars on total synthesis, and there's probably double the amount of introductory retrosynthesis on YouTube that you can find. But I think today what we really want to do is work through a total synthesis in real time. And so Noah and I have prepared some retrosynthesis for a molecule, as well as forward synthesis. And today what we'd like to do is really have an open discussion about why we decided to go through a few paths, whether or not the steps that we include would work, and perhaps some insight on individual steps, whether that has been conducted by Jeremy or Noah, or if they've heard from other people about these steps. And so really looking to get into the mind of a total synthetic chemist. Jeremy and Noah, I don't know if you guys want to introduce yourself and say anything, but I'll let you guys open the floor.
Yeah, sure. I'm Noah, as Aidan said. I work with Seth Herzon here at Yale, and my whole life is total synthesis, and so I'm glad Aidan sort of reached out and asked me to work on this pilot show with him, because it's really interesting to really think about these problems in a more theoretical, academic type space, rather than in the lab on a project I've been nose deep in for 3 years. So this is a great opportunity.
Yeah. One other thing is I should mention, if you haven't seen it yet, Noah's now a co-author now on a total synthesis of secure amines, and you can find that in Science published recently. I know he's not one to really brag right now, but if you haven't checked it out, please do. It's definitely an awesome total synthesis and quite a lengthy story. I'll just put it at that.
Appreciate it.
Professor May, I don't know if you want to say anything before we get going here, but.
Oh, sure. Just so my educational background is got my bachelor's degree at the University of Utah, did research with Peter Beal making RNA nucleotide analogs for mechanism probing of an RNA editing enzyme. Then I was one of the first students of Brian Stoltz at Caltech, and it's where I did my PhD work, and did a mixture of supramolecular recognition, host-guest chemistry, and mass spec for doing chemistry in the gas phase, total synthesis of the communescents, bisindole natural products, as well as methods based on carbene chemistry. I did my postdoctoral work with Sam Danishevsky, working on 3 different molecules there, and then started at University of Houston in 2008. Yeah. So that's where I am now.
Still doing, methodology studies, and great Nature Comms paper out recently. I'm making those, the quad centers, I believe, correct? And I remember coming in as a first year, and you were, I remember Po Kai was, hard at work at those. And it's really cool to kind of see it come full circle now. But yeah. As the audience can tell, we have a lot of background in total synthesis. My background is in organo transition metal catalysis, so I virtually have no experience with total synthesis other than Professor May's class and our project at the end. So I'm really looking forward to this and seeing how much I kind of retain, but also if I can offer a new perspective, I guess maybe, I don't know, an intermediate perspective. So for those that are just following along, trust me, you're probably not much better than me at total synthesis, but it's going to be really fun today. So I guess to kick off, I'll introduce the molecule. So I think I'll start sharing my screen now. And let's see. So let's share the screen. And I believe I have it up here. So hopefully you guys can see that. This is Bipolarolide D, which is a natural product with a 5-5-5-5-5-5 tetracyclic core. And it's quite a beast of a molecule. And I don't know if Noah wants. Let me see. How do I see? This is where I'm learning still. I don't know how to stop sharing my. Oh, here it is. Okay. So I don't know, because when we're picking the molecule, it's arguably the toughest part. Deciding what molecule you're gonna do, and I don't know. Noah kind of showed this molecule to me. I don't know if there's any first general thoughts on the molecule structurally. I don't know if anyone wants to kind of add anything to that or as to why we chose this, but to me it was kind of random. But
yeah, so in undergrad I worked with Jim Frederick at Florida State, and his work is sort of around this ephiabolin type space. And so most of the known ephiabolins up until that isolation paper have been in this realm of a 5-membered ring fused to an 8-membered ring fused to a 5-membered ring. And there might be some other cyclic appendages like a sugar or a spirocycle somewhere along that scaffold. But this isolation paper came out, and with a whole bunch of ephiabolin-like intermediates, and then some ones that to your eye don't look like it. They have these 5-5-5-5 sort of fused ring systems, but when you read about the biosynthesis in the paper, they kind of come from ephiabolin-like intermediates. And I picked this molecule because I was like, oh, it's low molecular weight. There's not much going on in terms of oxidation. This should be pretty simple. But this is where I'm still learning as a chemist, and I'm an alkaloids chemist right now. That's what I do. Our group doesn't have any specialty, but I make alkaloids, and I think about nitrogens and how tricky they might be to add different reactants to. I think about halogens. I think about aromatic systems. My brain is not set up to think like terpenes, and so I thought this was a great problem because it feels like I'm starting grad school again. It's a completely different scaffold than what I'm used to. And so I thought, let's pick the lowest oxidation, lowest molecular weight member of this family, and this will be a lot easier than the other ones. Not the case. I think multiple contiguous quat centers with specific chirality makes this molecule quite challenging, but also quite interesting. If you haven't seen already, there was a recent synthesis, I think, of Bipolarolide D, which is an even more caged, nasty molecule. It came out in Angewant late last year, early this year. And I mean, that synthesis is just not applicable to this one at all, despite them being similar isolates. And so it's a really interesting family with a lot of diverse functionalities.
Mm-hmm. One other thing I'll say is we will definitely include the isolation paper. So for those that are curious about it, we'll have plenty of chem draws, but if you want to see the original isolation paper, we're definitely going to include that. Jeremy, would you like to add anything or about the molecule? Or?
Oh, I just love Noah's comments there. Synthesis is definitely a hydra of a threat, and one of those heads is nitrogens. They are bad; they'll get you. Unfortunately, you have other things like quat centers and ring strain, and so many other heads that are threatening you there. I don't know, Aidan, if you remember my first response when you sent me the molecule.
Yeah, like 3 or 4 stereocenters. You were like, "This is
It was the 3 continuous quat centers on the ring fusions, which are notoriously beastly themselves. But then one thing in looking at this more that I think I'm only appreciating now and thinking about the structure is every one of these 5-membered ring fusions will probably be introducing additional ring strain into the molecule because you're distorting the tetrahedrons going into those 5-membered rings. I don't know, did either of you try to build a model of this with your model set?
I did.
Yep.
And how easy was it to close those rings and keep them closed?
I mean,
you got to be clever.
Not easy to it's not easy to close, but once they are closed, it seems like it's a pretty
Do you hear the creaking of the plastic?
Yeah, right. I'm afraid it's gonna break my model set.
Yeah, that's a sign that making these rings, because of the fusion kind of pulling back on them, it's not going to be the same as making isolated 5-membered rings. But getting back to kind of what Noah was saying, a big question I had is, there's some things like the quaternary centers that you can identify just by first inspection. But once you get into doing the retrosynthesis, you find problems like, oh, we should be able to make that bond. And you go into the literature and like, nobody's done it, right? So was there anything as you got into the retrosynthesis that you found out was likely to be more difficult than you expected it to be?
No, do you want to take that first?
Yeah, I mean, obviously, like this molecule it just has a lot of secrets, I think. And everything from this unsaturated enone that we'll show in a second, but like every ring has something that you would not expect. And this was a molecule where often my approach to retrosynthesis is like, I take a couple days and just fuss around trying a forward route, trying a backwards route, just understanding what my problems might be. And then I realized after doing all this forward route chemistry, I have all these great ideas. And I'm like, no, it doesn't. The retro says that this will not work. And so things like that primary alcohol is not something that you would think it's simple, but it's not. Things like the methyl group, there's a wedged methyl group on the molecule that can be a curse if you can if you have a tough time installing it, but it can also be a blessing because things like that can guide the rest of the rings if you're careful. And yeah, if you look at the other bipolarolides, it doesn't have the quite same oxidation pattern, even in the same sort of tetracyclic system. And so everything.
I don't know if I can give quite as good insight on that. My impression is this is all new to me, so I don't really have like a good sense of what is challenging, what's not. I guess with that though, I think, but I will talk about that when we discuss the retro. I think now probably a good time we'll hop right into the retro because I think I'll be able to kind of walk you through it. So I guess I'll go first. So let's see. I'll start sharing my screen again. Let's see. So I think, yeah, okay. All right. So this is gonna look a bit wonky for a second. But
do you want to just pause periodically for us to ask questions, or do you want us to interrupt you?
Yeah. Interruptions will definitely be welcome. So I assume you guys are able to see my screen now. You're able to see everything. I don't know. You guys are actually. What's weird about this? I'm sharing my screen. Is I have the inability to see Jeremy and Noah now, which is kind of weird. But let's see.
We'll just make faces at you the whole time.
Yeah, right. But all right, I'm gonna assume you guys can see it. So in the top left here, so this is Bipolarolide D. And I guess my first impression was, you see the tetracyclic core. And actually, by the way, one other thing I'll say is that I have so much scrap paper. So like, if you think that this is like my first shot at this, that you're like wrong. I literally had so many shots at trying to work it out, but like a publication, you're not going to show kind of what really works, I think. So, anyway, I have the molecule here, Bipolarolide D, and I think my first impression was that there was two obvious disconnection points, I think, at this point. So one is this bond right here, and then as well as this bond as well. Why? I don't really have a good sense of why. I just kind of took it back a step. And then from here, I was thinking, all right.
Aidan,
yeah, go ahead.
If you go back to Corey's The Logic of Retrosynthesis, one of his principles is disconnecting at bonds or atoms that the greatest number of rings share. It's a higher powered disconnection. It's more strategic. And I think that's putting your intuition into words.
Okay. Yeah, thank you. Yeah, thank you for providing that.
That's
definitely also, I think. Yeah, go ahead, no.
I was just going to add, if you read the biosynthesis, this is how they suggest this bond is formed.
Yes, they do. They do mention
So
that.
I didn't know if you read that or not when you proposed the retro to me a couple weeks ago. I didn't want to say it because I wanted to see if you wanted to change anything, but it lines up
Yeah.
with how they think the enzymes do it.
Yeah. Plus I just think that I was like just looking at that, I think it just might be the easiest disconnection because that's just my impression of it. So when we get to this intermediate now I'm thinking, all right, olefin metathesis, which kind of brings you back to this fragment. And so this fragment brings up one really interesting point that I love bringing up to Jeremy, and that is if you disconnect, in between these bonds here, you're basically left with two cyclopentanones, which I know are Jeremy's favorite fragments. I'll never forget in the class in reactions and synthesis class. I'm paraphrasing here, but you basically said if you have a cyclopentanone, there's that you can basically put on any functionality you want. There's a way to do it stereoselectively as well. I don't know if I'm misremembering that, but I don't know if you want to comment on that. But I'm pretty sure I remember you saying something like that, where it's like you can make cyclopentanones.
Close enough, yeah. It gives you control over pretty much every position.
Yeah.
It was in reference to Stork-Danheiser chemistry, specifically, where you have the vinylogous ester manipulation.
Yep. And as someone who watches a lot of Phil Barron's lectures, I'm going to access my inner Phil Barron here. But, if you asked a 5-year-old how you would disconnect this molecule, they'd probably say somewhere in the middle, these bonds right here. So I think that this is kind of twofold. One is, I think a double decarboxylative cross-coupling would work with these carboxylic acids. It's relatively new science. I don't know. I don't know if at least going to the paper, the publication to where it came from, you're able to get pretty complex carboxylic acids to couple. And in the examples where they have a stereoselective carboxylic acid, it's able to retain its stereochemistry. So I figured that, I don't know, hopefully this would work. So I don't know if Jeremy or Noah want to chime in here, but figured I'd, talk about this.
Go ahead, Noah. Looks like you want to say something.
No, absolutely. I think, we didn't get into the rest of the retro. So we're going to 100% assume fragment A and B are synthesizable. And I'm not implying anything else, but I really like this disconnection because of the front-facing vinyl group you have next to the ketone. That will guide the stereochemistry of the decarboxylative cross-coupling. Yeah. Because that fragment B would basically be pushed to the back face preferentially for that coupling because the sterics on the front face are blocked. So I think it's a really great way to control the stereochemistry of that reaction, just using the innate facial selectivity of chemistry.
Yeah, I glanced at this briefly. Is it nickel 1,3 or nickel 2 chemistry? I forget.
I think, according to the paper, it's kind of a mixture of all of them. I'll also leave. We actually, one other thing I'll mention is that we actually did Synthesis Workshop did a complete mechanistic study. We actually had on oh my god, I forget the name. I forget the name of the gentleman who did this chemistry. So I'm gonna leave that in the description. But yes, it was Max. Yeah.
Shout out Max.
Yeah. So it's I believe it's like nickel 0, nickel 1, nickel 2. I don't think there's any nickel 3 involved.
I totally agree with what Noah said. I thought, that should be great. I always worry about nickel chemistry where there's kind of these organic radical intermediates with the proximal enone, because then you get allylic radical functionality, and that can allow for transposition to another position. Now, you may have going in your favor here that the conjugation in the enone is going to stabilize that, allow you to keep your coupling side at the same carbon. This is one of the things I love about synthesis that drives people crazy is, we come up with these ideas and there are these huge unknowns where we don't know what the cross interactions with other functional groups will be. This is an idea. This is a hypothesis. Synthesis is hypothesis-driven research. A lot of people think, oh, you can just make anything. You come up with these ideas and you know what happens. But that's only because they don't see the hypotheses that we're wrong. They only see when it works out. So they really think we know what we're doing, but we don't. We have to explore these complicated situations so we can learn more about the interactions of specific catalysis with different types of groups. So I love this hypothesis. It would be fun to try. Certainly you would try it with a simplified system before going whole hog with this one.
Right. Yeah.
But yeah, I like it.
Yeah, I think, again, if this step didn't work, basically my synthesis is out of the water. So, but one other thing I'll say is I actually made a note here because you're right about the kind of all these olefins really. I feel like any sort of late stage Segusa-Ito oxidations could kind of mitigate that problem. So I could this could be fully saturated and then come back and maybe do a Segusa at the end to avoid these sort of enone type structures. So hopefully that would be a way around it. But yeah, I kind of just left it in here for this. But for the viewers, you could do a Segusa-Ito oxidation later on if you wanted to keep it fully saturated.
And Noah shows a nice protecting group for that enone too in his picture. Yeah. So
Excellent.
We'll see that.
So assuming that we could get this to work. All right, I'm going to kind of take this back now to the two fragments. Now, I will say that we didn't really discuss, percent ideality or, is this green or are we really we didn't really have that thought. We want to try and converge as many steps as we can, but that was not necessarily a priority for us. So,
can I get on my soapbox about that?
Yeah, go ahead.
There's a time and place for metrics, but we're trying to explore creativity, both in this sort of podcast, but in real life too. There's a creative human element to this that cannot be measured by metrics. If you're pushing the boundary and frontier of science, to me, that's the goal. And not everyth's Taxol. Securamine that I just made, it's not Taxol. I'm sure you can make it shorter. The point is the chemistry inside of it creates a story beyond just the numbers telling you something. And that's not to discredit the percent ideality type argument, but it shouldn't be a reason to look at your synthesis and be like, there's too many steps, right? I think it distracts from the point. So that's all.
Yeah, I think that's well said. But so going on through fragment A, all right, so this is where I had a bit of trouble. So originally, what I was going to do is this fragment that I'm kind of just circling right now. I originally thought maybe I could use some sort of James Morgan work, which is Noah and I were just kind of talking with him on recently, or talking about his chemistry recently. And I thought maybe I could do some sort of Enantioselective cross coupling, where if I had a B pin here, and I had a vinyl triflate or vinyl iodide, I could do some sort of stereo selective cross coupling, but ended up just not really working. But the problem was I was already too deep into the synthesis to kind of just avoid this now. So I went to Twitter, and I'm going to come back to that later on. But so I think that the way to get more people involved is, I'll kind of have a fragment and I'll put it out on Twitter for people to get involved. So if you'd like to get involved with this type of stuff, make sure you follow us on Twitter, and we'll give you guys shout outs for this synthesis. But okay, I can't go from I couldn't find a way to go from here to here. But assuming I can make this fragment, just a few oxidation manipulations, I think I can make this fragment from a 5-exo trig, which would go back to here. A deep protection of an alcohol and oxidation would give you this fragment. I don't know if you could do some sort of selective Wittig reaction to install this alkene here. I was looking through the literature. I was kind of hoping I'd find a direct, because I have a little alcohol here, so maybe I could direct it. I don't know, but that would just kind of give you back to this epoxide ketone that you could make from an asymmetric epoxidation, I think, from the starting material. Any concerns from Jeremy or Noah here? I don't know.
this is a general thing that no one thinks about unless they're doing this. Volatility matters. It makes precedent in chemistry that people do in industry really hard to do in your own lab on small scale with a confined budget. And so some of these simpler intermediates could be completely workable. Like you can completely work them, it could be fine. But something, until you maybe make the carboxylic acid near the end, you'll always have to be thinking about how volatile is this? Are my yields accurate? Can I even work with this thing? But if the chemistry works, and volatility is a secondary factor.
I have a comment on your let's see, alpha beta, this gamma chiral enone, yeah, right there with the free hydroxyl to the left of that.
Oh, right here.
So my initial thought would be that should be available from an aldol condensation. And then you're working with stereochemistry with a non-cyclic stereocenter, and that's often more straightforward. But then you have this desymmetrization almost with your ketones, and you have to control which way that aldol condensation goes. So it gets fiddly really quickly. So that's one of those side traps that can grab early practitioners. That's the exact type of building block, though, that Luke and I were trying to come up with a 2 or 3 step synthesis for when we discovered the quat center formation. So that's how we stumbled onto it, is we were trying to make molecules like that because they look easy, but it's not trivial for those building blocks.
Yeah.
So we'll get back to that. We'll tackle that again. 6-membered rings we have down no problem, but the 5-membered rings are a little harder now.
Yeah.
As far as that last step goes, we'll probably need to somehow protect or mask the carboxylic acid. But when you have that, there are certainly alpha arylations of enones known. I imagine you might be able to get some of that chemistry to translate into alpha vinylations if it's not already known. So it would require some extrapolation and some methods development. But that's one of the other really important aspects of synthesis, is you get into problems like this, and then that drives new catalysis, new reactions, and it really drives the field forward as we try to do this.
Yeah. Yeah, that's an excellent point there. I couldn't really find anything. People in the comments, let us know. I couldn't really find anything on doing some sort of alpha vinylation. So especially at least like stereoselectively. So I wasn't really sure. If people know a way, please let us know. I didn't.
Well, you have that acid there that you could do it diastereoselectively.
Yeah, diastereoselectively.
Yeah, and maybe we'll get into it with the forward synthesis part of it, but alpha alkynations are known of ketones, and so you can do a hydroalkylation with selective Markovnikov versus anti-Markovnikov selectivity on alkynes, and that might work really nicely. So don't worry about the vinyl. Take it in at the right oxidation state and just add different groups to it. But of course, we're thinking about conciseness, about convergence, and what you have drawn is the most concise disconnection if possible.
Yeah. So thank you. Yeah, thank you for that insight. I look forward to kind of doing the forward for this, because we actually got some pretty good suggestions, I would say. So thank you to the community for helping me out. Okay, so moving to fragment B then. Is this the right? Actually, do I have the right one up? I think I do. Okay, so I have fragment B here. I think you can kind of, like these sort of Sagusa-Ito oxidation types, I think you could do late stage. So if, I'm just saying for the viewer, like, I wouldn't be too worried about this, because maybe you could just do that at late stage. But anyway, also one other thing I should say is like this sort of alkene, this pendant alkene, you could probably also do late stage, I guess. I mean, I don't know if you really want to carry this through, or actually, I don't know. That's an interesting question that I guess ask you guys is like, would it be easier to install like something like this through a Vidig at the very end, or carry it through a total synthesis? Like, I don't really know. I don't have a good answer for that.
I think you'll see my answer to that in my chemistry.
Okay.
And a hint is that this scaffold, this exact alkene that you're trying to make, is known in its totality. The synthesis of that exact fragment, that disconnection, is known and has been used for beta additions to enones and also cross couplings, I think.
Okay.
So it looks like a terpene. It looks like a sort of isoprene type intermediate. Whenever I see the isoprenes, because everyone makes terpenes, whenever I see an isoprene type thing, I just straight up reaxes my exact intermediate and just see if someone's made it.
Yeah, this side chain is pretty common in
Okay.
I've seen very similar ones in steroid chemistry, but that stereocenter even reminds me of the side chain on like vitamin D. It's pretty common in terpene chemistry.
Okay.
So agree with Noah 100%.
Okay. All right. So
one comment though is I forgot to go and look this up. So you and Noah have opposite stereochemistry for the alkene on that side chain.
Oh shoot!
I think I drew it wrong.
Okay.
I must have drawn it wrong. That's my fault.
Okay.
Okay.
Because this exact reaction you're doing here, instead of avidic, Kishi has this selective formation of tri-substituted alkenes with Horner-Emmons-Wadsworth. Emmons, Horner-Emmons-Wadsworth, whatever way you want to say that, to make that tri-substituted alkene with an ester there that could later be reduced. So that you can do that.
Okay. So that's no problem then. Yeah, it's good to know. I mean, yeah, I imagine someone had to have done this sort of vidic.
Yeah,
so
if you do it the other way, where you're trying to make a tri-substituted ketone, or tri-substituted alkene from the ketone, that's a bit more of a struggle. And in those, it's almost easier, like Noah was saying, to do the alkylations of the alkyne. Montgomery has some real nice functionalizations of alkyne. Peter Whipf, some of those things.
So, the vidic, again, it can be done. So I'm not going to harp too down on that too much. But from here, I'm thinking, all right, some sort of cross coupling here, because that's kind of where my background is and kind of my first thought is here. Some sort of cross coupling here, which would bring me back to these two fragments. And in this paper, they I actually think they have this sort of exact fragment where it's like an alpha bromine, and then you do with a stereospecific kind of electrophile. Now, I actually don't know how I could make this, but that's like I saw it in their paper, so I was like, all right, I'm just going to take it through. Now, from here, it gets kind of, I was like, all right, my first inclination is like, all right, some sort of cuprate to take it back, or Gilman cuprate addition, take it back to this third fragment. And a few protector group manipulations and oxidations. I'm gonna go all the way back to this fragment here, because I think actually no, I'm gonna go to this fragment right here because that's just a Segusa-Ito oxidation. Again, maybe you could do the Segusa-Ito later on, but having this fragment, so this is surprisingly kind of a challenging substrate to make, I guess, or. In 2008, Hoveyda came out with this Enantioselective methylation addition to the cyclopropanols, and I figured I'd just use that. So we'll talk about that in the forward synthesis, but that would take you back to here, which then can be, this exact substrate can be made using this method that I have here that from this paper. So taking this cyclopropane, with some cobalt, you can make the cyclopentenone, and then you can buy these starting materials. So, any general comments for, I guess, let's say this retro here?
That Olivier paper is pretty cool. I looked it up because I'm like, what are you doing with a hemiacetal as a starting material? But we all know cyclopropanes are weird, and this is an example that the hemiacetal is stable and isolable for the cyclopropane. It wouldn't be in anything else, but for this one it is. That's really kind of cool.
Mm-hmm. very, very, very proud of this one because I guess like this, obviously these types of fragments are, really important. People would like to have easy access to these, so this is a pretty robust way of making them, and you can get pretty different. You can get various substitution patterns on this alkyne too, to make these sort of fragments.
Yeah, that rearrangement is pretty interesting there.
Mm-hmm. And we'll definitely discuss that a little bit more in detail when we talk about the forward. But no, I don't know if you want to anything out on the retro before moving to yours.
Yeah, I will just say, and you'll see this in my chemistry as well. It's very gratifying, having because our lab works on molecules that you don't see in literature very often, and so it's very gratifying to work on molecules like this where you back out to an advanced intermediate, but someone's made it before because it makes you feel like you're on the right track. That you deduce with your own mind a retrosynthesis that goes back to an advanced intermediate that someone else can make, to make a whole new product. So yeah. I like it. I think one thing that would make me a little nervous is you after your Gilman addition, you have this basically this pretty electrophilic 1,6 dienone. And so just again, you don't know until you make it what's going to happen. But it's very, very electrophilic, very electrophilic.
Yeah. And this is definitely something we talked about before. I could probably remove this double bond right here. Mm-hmm. And then, kind of carry that through. And then a late stage stigazito maybe, right? I think.
If you're doing a conjugate addition there with the vinyl group, that double bond won't be there.
Yeah.
You have to reoxidize to get it back.
Yeah, I should. It really should look like this, honestly.
I will make one. The cross coupling is the way to go here, for sure. Because when I looked somewhere else, I thought you were doing like a secondary electrophile with an enolate, and that wouldn't work. But yeah, the cross coupling is your best bet if you can get it to go.
Mm-hmm. Yep. And I one last thing I really like about this is that you have a very known precedented way to introduce your first stereocenter. Your first quaternary stereocenter at that.
Oh, this one down here?
Yeah, and what's nice about that is the earlier and the more precedented you can introduce those stereocenters, the rest of the chemistry, especially on 5-membered rings, will kind of just follow that stereochemistry, and you can guide the entire rest of your synthesis based on it. Yeah. And that's a criticism I have in my own route, which is you'll see if you're paying attention, there's one step that I propose that's extremely problematic, and I have a way around it that is pretty precedented, but I guess I'll share.
Yeah, I was to say, let's hop into yours now.
Okay, so how do I choose? Okay.
Yeah, if you share, so share, then screen, and then
spoilers.
Yeah.
Okay, you guys can see my screen?
Yep.
Okay.
Yes, we can.
So I just made some slides because I think it's easier to break it up that way. This is how I drew the molecule, and I drew it wrong. Jeremy was right. This alkene is the other stereoisomer, but you'll notice it doesn't matter ultimately based on this retro. You can draw it the other way and get to the same disconnection. Yeah. But yeah, I drew it this way because in the isolation paper they drew it this way, and just for the sake of the viewers, if this is more educational for them, I wanted to keep that similar. But here's my simplified retro. I thought that I like to do later stage deprotections in my synthesis. I try not to do functional group modifications. And so to me, bringing in the oxidation through a convergent manner is great, which ultimately leads you to deprotections of oxidized scaffolds at the end. And then from there, this was a big thing. This top ring is quite tricky. But I thought that if you could get to a scaffold that had defined chemistry that was unable to epimerize, you could perhaps alleviate some strain in the molecule by taking an endocyclic tetrasubstituted double bond and doing some sort of first a decarboxylative cross-coupling to install the quat center next to this ketone on the left. And then that intermediate could be leveraged to do a conjugate addition into this ketone to alleviate some strain.
Wait, no, real quick. Are you supposed to be on? Oh, we're still on your title slide, so I don't know if you're supposed to be.
Did it move? I can also. What do we see now?
Okay, now you're on slide 2.
Okay, yeah, I'll just go with this then. I was in presenter mode.
Okay, yeah.
Yeah, but anyway.
Yeah, we're still trying to figure that. It's kind of weird to share screen on this. it's a bit finicky. Still working that out, but
yeah, it's whatever. So yeah, I'll go back to this. My retro, I just start with the
there you go.
deprotection. I think the alcohols are pretty innocuous as long as you protect them correctly. And then the center ring at the top, I want to take it back to a decarboxylative annulation, because this carboxylic acid group, I don't think it's going to readily epimerize if you make a radical, just considering some of the steric effects of the molecule, but also this 5-5 fusion. Oftentimes you do see sort of 5-5 rings fused with a syn sort of orientation. And so I thought you could do some sort of decarboxylative cross-coupling to make this quat center. And then from there, that sort of resultant group can have a functional handle to do a beta addition to alleviate strain into this corresponding ketone. Now, I flatten this out a little bit because it's easier to talk about, but this, I think, can come from a selective Pausen-Kahn reaction to rapidly generate a number of bonds in a very complex way. And I have some rationale as to why we get a specific diastereomer out of this. I'll talk about it. But using this chlorinated intermediate, Andy Evans at Queen's University just showed in a wonderful lecture at Flowhead that these chlorinated alkynes actually enable these reactions to go at much lower temperature. You get nice selectivity out of them, and it installs a cross-coupling handle when it's all said and done. From there, I found this reference where you can make these cyclopentadienyl adducts with a bromine here, and the chemistry is pretty precedented. The issue is getting it off requires like extreme temperatures, and I don't trust complex scaffolds with that, so I decided to use a TMS cyclopentadienyl species, which is a lot easier to remove, but still very stable. And what's nice about this is this, you can do it racemic, and there might be a problem with that. I'll talk about that later. But you can also make these asymmetric just by adding 2 steps to the route. What's nice about this fragment here is that this cyclopentadienyl adduct, this alkene actually hovers way over the enone alkene, making every single addition that you want to make, as long as this group is on here, go to the back face, which again guides the stereoselective alkylation chemistry. So that's kind of what I was thinking for my retro.
That was sick. When I posed the fragment synthesis to Twitter, I got a lot of Pausen-Kahn reactions, and that's crazy. Like those types of name reactions don't really come to my mind.
It's a trap.
I can't see those. Like I've never been able to see like cyclizations that well. I can't really see. It's so hard to see the retro for those.
It's a blessing for you, because the issue is when you start seeing these reactions, you do pattern recognition with your lizard brain, and it's like, oh, Nazarov, oh, Pausen-Kahn reaction. But those reactions are not simple, and the selectivity is quite challenging. And so if you're going to propose those, you need to rig the system exactly right, which is so dang hard. And that's what made this retro so hard, because I'm like, I want to do a PKR. I want to do it. I saw Aidan synthesis. I don't even want to touch it. I don't want to get anywhere close. I want to have a good conversation about this. And so the PKR, I think you can rationalize every single bit of chemistry out of it, but you have to really, try it ultimately. Yeah. And you get pretty late stage, and if it doesn't work, your entire synthesis is blown up. So it's a blessing that you do not see that.
Anything you want to add, Jeremy?
Oh, just PKRs always look like they work, but once you start doing it, you can get isomers, you can get some selectivity issues, and in talking with people that have done a lot of them, they often just fail for who knows why. So yeah, it's tricky, but they're also beautiful reactions, and they work in just so many wonderful cases that you have to at least consider it, I think.
Fair.
Right. Yeah, I think one of the most inspiring things for me as a chemist in undergrad to go to grad school was seeing Sarah Reisman's ranitidine-ranitidol synthesis, and how impressively they leveraged not just a Pausen-Kahn reaction, but further oxidations thereof. And these are not molecules I work on. I work on, again, if you want to read it, halogenated alkaloids. So for me to wedge something from that inspired me to be a chemist into this synthesis, it's kind of like a bit of my personality going into the retro.
Yeah. Was that your complete retro, or you want to move into?
That was
So,
it. I like to keep it short
okay.
and sweet. I think the big
Yeah.
strategic points are there. I think there's a cross coupling. I found the exact same no shell paper, but I used a slightly different intermediate. And we'll talk about that when we need to.
Yep. All right. So I guess we'll switch over to the forward now. So let's let me so I'll put this away. Let me open this one up. There we go. All right. So for the forward, we'll probably, we'll discuss where important steps are needed, but generally, and also I should mention too, we're not necessarily going to talk about, actually, never mind. Okay. So if you guys can see my screen here, and so here's the forward synthesis. So if you remember, I couldn't really figure out a way to make fragment A, but if we take this forward though, I think from commercially available, you do. I hopefully so. This is funny because I really hope I chose the right catalyst to do this, because I had a 50-50 shot, and when I was doing this, I didn't have my model set on me, so I couldn't see if I actually ended up making the right epoxide. Jerry, is this the right conditions for this epoxide? I forget. I hopefully I didn't have my model set. I couldn't model it.
Yes, but you will get some resolution in there.
Okay.
So one of the enantiomers of your starting material will react faster than the other. Mm-hmm. And the enantiomer that reacts more slowly will often give poor selectivity for the epoxide.
Okay.
Now, and so I forget what it is with the methyl vinyl alcohol. The phenyl vinyl alcohol gives very high differentials. The methyl I don't remember, but you would probably want to do the kinetic resolution here to get better ER for your epoxide. Okay. There's another way to do it. I'm trying to remember if it works with just, unsubstituted enones. Jorgensen, like 15 years ago, has some beautiful organocatalytic epoxidations for enantioselective epoxidations of enones. I forget if you have to have the beta substituent there or not. I haven't looked at those in years. But yeah, there's a way to get, I think, the epoxy ketone here. Yeah. I think Noah's comment before about volatility does come back, and that you're going to have to distill all of these things, and so they need to be thermally stable as you go forward.
Oh, geez. Okay. Yeah, something again that I personally don't really consider is, the problems of volatility, but also like I don't even. My general impression is like the more if it's a tertiary or has two substituents, then the epoxide formation is probably easier, like more substitution pattern. But I don't know if it really works on this. How simple this fragment is. In any case, I think there is definitely a way to make this an anti-pure epoxide. Though I'm sure there's a way to do it. But then through an oxidation, pick your favorite one. I just desmar and pyridine. I don't even actually know if is that a simple. Well, from the perspective, let's say of large scale, like how would someone do this large scale if you wanted to, like what's the recommended oxidation?
DNP is kind of expensive.
Okay. I figured that, but I'm not sure.
You could do a catalytic dehydrogenation, or the Swern reaction is actually quite cheap. DMSO, oxalochloride, triethylamine.
Yeah.
Something like that.
Okay.
Yeah. The issue with the oxidation chemistry on that epoxide is that a lot of things that oxidize alcohols may react with epoxides or activate epoxides. And so if you were to do something with oxalyl chloride, you may end up getting like a Payne rearrangement type reaction, and there's a couple of tricky bits there. So I almost think that starting with the ketone, if you could just start from the unsaturated ketone, that may mitigate some of those issues.
Fair. Okay. And then Vedic. Listen, I'm gonna pray I get the right region selectivity here. But I was looking through the literature. I didn't really. Is there a way that you can like, if let's say this is like unprotected for a second, is there a way to like direct Wittigs? Like, I don't know. It'd be. I don't know if that's possible. I don't know. I have no idea.
Not without there being something else to do that. But also remember that Wittigs are kinetic controlled. So, yeah.
Okay. Well, I just pray. I just pray I get the right radioselectivity here. But then I think through a deep protection and then another oxidation, I get this. And then here's where I'm thinking, ready for, I think it's a 5XO trig here. And I don't actually really know the good conditions for this. I mean, obviously, I want a base to deprotonate, but also one, that'll avoid the other acidic protons. And then some sort of Lewis acid to activate the epoxide. And then hopefully you can, and then on acidic work, you can maybe quench it. I have no idea how easy this step would be, or if it's even possible. I don't know if you guys want to add anything to this, because I have no idea.
The idea of coming in with something like a frustrated Lewis acid base pair, or Bronsted base acid pair, that's interesting. So, like, say you have lithium TMP, and then like BF3 etherate or something else that, like triphenylborane or something. So you can have the base and the acid in there at the same time. I think there are some precedents for intramolecular enolate epoxide opening. I would have to go back and look. Intermolecularly, they don't work, but intramolecularly, there may be a precedent or two that I'm thinking of.
Yeah, I'm praying that some sort of intramolecular would work here. I also, something I realized too, I didn't realize how actually...
Yes, there is. I'm remembering now, because there are two precedents. I looked these up last year for just regular lithium enolates opening epoxides, because normally that doesn't work. So one is with stabilized enolates, where you have 1,3-dicarbonyls, and you can just cook them up. And those there are examples of them using epoxides as electrophiles, and the other is intramolecular. So it has been done intramolecularly. So I think it might actually work.
That's what we're going for here. These steps would actually work, and then I think from here, just an oxidation. Probably something that will avoid these this great alkene right here. I don't know if these are too harsh. But again, if it does get oxidized, you could probably just...
Jones is too harsh.
Yeah, I figured Jones should be too harsh.
You could do 2-stage. So the pinnock oxidation was specifically designed for not to harm alpha-beta unsaturated systems.
Really? Okay.
If you get to the aldehyde, then the pinnock would take you to the carboxylic acid, certainly.
Okay. So this definitely can be done. And then at this point, again, this is where I wrote to Twitter, because I really just couldn't figure out how to get from here to here. If we dive deep enough in the literature, I'm sure you can find something like this, where some sort of cross coupling. I'm sure it's somewhere out there, but I couldn't find the exact conditions here. But from here, I actually want to go. I'm going to switch gears a bit here and go to Twitter, because, like I mentioned, I couldn't figure out how to make fragment A, and so we opened this up. I opened this up to the floor and was like, okay, let's see if some other people can make that. So let me pull those up now.
Yeah, man. As a Twitter sidebar, I don't care how many awards you have. Twitter as a collective might be smarter than anyone out there. Like,
right.
I don't know about X, but Twitter for sure is it's a really good resource for science.
Really. So let's share screen here. So let's go here. All right, cool. So this one was submitted by Ruben Migueles through my DMs. He sent me this, and this is the first time that Jeremy and I think Noah are both looking at this. So, assuming you can make this fragment, I don't know how you would do that. But then looks like some some base, and then you attack the acyl chloride. You release the SO2, and then you're basically preparing for a Nazarov reaction. I'm gonna maybe
that base. So you have an extremely acidic proton between your ester and sulfone. It's a
right
Lilith,
here,
and it's got 2 electron withdrawing groups on it. That's maybe you're deprotonating that first and then doing the lithium halogen exchange to get to the double anion. And that's the goal. No, because once you deprotonate there.
Yep.
Oh, no, you're okay. I was worried about the protected ether as a potential leaving group. No, you might be able to get that dianion. The sulfite might leave. That's right nomenclature. The SO2 minus.
SO2.
Yeah, I'm a little worried about
it.
I love cyclic butynyl sulfones because they're precursors to like butadienes.
Okay.
All the reactions, so they thermally break down. So I think it's a really cool idea from that perspective. I worry about that acidic proton and what it will do.
Yeah, that's definitely a
double anion might work. It might be stable enough at low temperatures.
Yeah, TBLE it's a workhorse. An alternative, I like the Nazarov. I think it's always a nice way to make those rings. You can just take the top right fragment and make that from a stili on an acyl chloride. So if you take the commercial acetyl chloride and just chop the bond between the carbonyl, that one right there.
Yeah,
so if that is an acetyl chloride and the other species is a stannane or something, you can do a stili there, or even a carbonylative stili if you want, and install that in a maybe less problematic way with as we refer to the base.
Yeah, I think stili would be great here. Such mild conditions, great. I saw a lot of Nazarovs. A lot of people are suggesting Nazarov reactions here. I don't know if you two have any experience with the Nazarov reaction. I don't know if like how robust this type of reaction is, but I don't know.
It's beautiful work, and that alpha beta substituted cyclopentanone is a really nice substrate for it. The tricky thing with the Nazarov is getting the alkene in the right place. I'm not sure if that acid would favor the alkene on the right side instead of the left. I would have to go back and look at the precedent.
I have no idea how you control the stereocenters here formation. I don't know if maybe given the star material.
Trans is preferred.
Okay.
But it would be racemic, yeah.
Okay. So that was one of the suggestions. The other one is, let's see. So let me stop sharing this one, and then let me come back in here. So then the second suggestion, let's see. Let's go here. All right. So this is from Colton Johnson, which
I love this one.
I love this one. When I saw it, I was like, this is great. So starting with Corvone, which, fantastic. You install the alcohol. You put in your, is this a nitrine? I always forget the nitrine.
No.
Diazo, sorry. Diazo, you install the diazo compound. Oh yeah, literally says it right there. And then, oh man, I forget this name reaction.
Wolf.
The Wolf rearrangement. Yep. It's just so cool. I gotta see. This is where I never would see this. Like I would never see this type of transformation here.
Me neither.
The author Colton did say that he's not really sure about controlling the I guess it would be the diastereoselectivity here, but great. This is so creative though that I loved it. Some oxidations, and I don't know what these two.
Yeah, it's Christina White's chemistry. Yeah. I like that application of it.
And such a great precursor, like great starting material. So
buy your stereo center, purchase it. It's the best way to get it.
Yep. Jeremy, any thoughts on this?
Oh, I love it. Well, I love carbenes and diazochemistry. So the wolf is beautiful.
Do you have any experience with like a wolf rearrangement, or is it how robust is that kind of?
I didn't, but I was working on carbene chemistry from hydrozones while Richmond Sarpong was doing a wolf rearrangement cope cascade for his postdoctoral work in the Stoltz lab.
Okay. Yeah. Well, this synthesis was extremely creative. So thank you, Colton and Ruben, for sharing that. And then I'll just quickly go through fragment B, and then I'll let Noah go through his. So let's see. Let's go to window and then go here. So I'll quickly move through this one. So with fragment B, basically I want to make this cyclopropane. And this is through, make it Grignard formation, and through this hemiacetal, you get this, and then through the Ikeno, I think, was the paper for reference 3. But if you use stoichiometric amount of this cobalt carbon monoxide complex, it'll rearrange to this cyclopenteno, this exact substrate. So really fascinating rearrangement here. Again, I'll leave all the references in the description so you can kind of go see the transformations for yourself. But reference 4, so this is the enantioselective methylation, I guess, or conjugate addition by the Hoveyda lab, which, over 10 years ago at this point. But I pray you can buy this Silver 1 NHC. If not, I don't
think you can buy it, but you make it pretty easy.
Okay.
Gilbertson Group makes it a lot. I know others have done it. So
so luckily then it's not too complicated then. But with this copper and trimethyl aluminum, so please be careful with this one. But you will get an enantioselective conjugate addition of this methyl group.
Just never let any drops of trimethyl aluminum fall on an oxygen balloon.
Oh, Jesus. Right.
That'll be instant fireball.
Right. It's I've handled trimethyl aluminum once outside the glove box for whatever. I don't even remember what I was doing, but I had to do it outside the glove box. That one's actually like scary. You need to be careful with trimethyl aluminum.
Yeah.
Really, you really should be using inside a glove box at all times. There really is probably no reason to take it outside.
There was a course of a year where I would make fresh Tebi reagent every week, a few times a week, because for our hydromethylation method, the only way to get it to work was to make it fresh. It was just better, and that requires an insane amount of trimethyl aluminum. And we're making this on scales where we could take from a batch and just use a batch throughout the week for our method.
Yeah.
It's spicy, man. If you can find a way to not use trimethyl aluminum in your life, do it. But obviously this reaction works, so use it. That's total synthesis is like we're limited by the chemistry that exists.
Yeah. Going forward, again, I've said this before in the video, but you could probably do a Sagusa oxidation later stages. I just kind of did it here, but I'm sure you could kind of rearrange the steps here. But we want to install the bromine, which through this reference here, you can get an alpha bromination, and it'll keep, it'll make this fragment. And I think, so this is where, so in my forward, I had this a bit differently. I did do I do a cross coupling eventually? No, I don't. Okay, so in this one, I don't have the cross coupling.
Yeah, the retro you did.
Oh, we talked about this, right?
Yeah.
Offline?
Yep, we did. I don't know. So looking at this now, right? If you add in the Gilman cuprate, you get the conjugation. I think you'll get something like this, right? This is kind of the intermediate. And then I just don't. Looking back now, this is probably not enough of a nucleophile to do SN2 type chemistry. Probably just isn't. But we can get around this by doing a cross coupling instead, I think, and doing a Gilman addition later on. But yeah, I don't think this SN2. Actually, do I have it even down here? No, I don't. Okay. In any case, I think it would have to do cross-coupling here, not through this SN2 type. I don't know if you guys have any thoughts on this kind of sequence right here.
I think Noah has it in his that's the Nichelle cross-coupling, which is really nice.
Okay. All right, so we'll come back to the Nichelle cross-coupling then. Let's see. So, and I think at this point, where am I? So I just do a deep protection and then a Wittig. Again, we talked about this Wittig before, though, so this is not really an issue. And then I did this part is kind of funny. So I did a Sagusa Ito oxidation and then a Luce reduction. So I can turn this cyclopentanone into an enol. I don't know if there's an easier way to do that, but this gives me fragment B, though.
That's why we're not doing metrics.
Yep, this is makes no sense to do the oxidation and then a reduction right after it, but hey, we're not here to talk about percent ideality, but that's how I was able to get it.
I kind of wonder in the headspace of Jin Kuan Yu, if you could, looking at that carboxylic acid you have on that fragment, or even if you first reduce the ketone to an alcohol, can you use those as directing groups for CH desaturation? I do not know, but you might not need the ketone as a function to handle. You might be able to probe a lot of stuff where you first desaturate, or you first reduce the ketone and then you desaturate next to the ketone. I don't know.
Yeah.
But you might get a lot of weird palladium chain walking type garbage, so who knows?
Yeah, generally speaking, I think kind of moving back, this is kind of a suitable candidate, I would say, for the double decarboxyl cross-coupling. So I think, so the notional cross-coupling to make this sp2, well, I guess, sp2 or sp3 center could kind of be done at a different stage. But so I guess my point is that you could have steps in different orders to get you the right. You'd have to really work on the steps of it. But in any case, assuming I get these two fragments, I think I'm ready to do the double decarboxyl cross-coupling, which, again, the reference here, but basically you just activate the carboxylic acid using a redox active ester. I don't even know if this is the right one, but you use multiple equivalents of the ester, and then you electrolyze with some nickel, and you get this cross-coupled product. Really cool chemistry.
For the first step, which acid are you going to react it with, or does it matter which side it goes on?
I don't think it matters, at least as far as my understanding goes.
Procedurally, do you have both acids in there at the same time? You only have one, right? So you make sure you get cross-coupling. Yes,
that's right. Yeah, so you probably you would activate one of them, and then chuck in the second, then the carboxylic acid. Yes, if I remember correctly. Yeah. So you activate one of them, then throw in the other carboxylic acid. I don't know which one would be easier to activate. I don't know if it really matters, but we get this cross-coupled product. Then through some of your olefin metathesis conditions, find your favorite one, and then through some, and then this is actually a tough step. So what I'm planning on doing here is that I got to deprotonate this proton right here, and hopefully that'll do that'll attack this alkene, and then you eliminate the hydroxyl, or if I need to manipulate the leaving group, I can, but I don't know if this step would work. Obviously, if I had base with this unprotected alcohol, I would just obviously, but don't really worry about that. But I don't know if deprotonating this amine would attack right here. Hopefully, they're in close proximity. I actually should have built a model of this, but
so
I don't know.
What you have a hydroxyl there on the right side. Are you making that a leaving group? So this is SN2 prime like, or would that be an enone? So it's electrophilic.
I was thinking more of the elimination route. So, deprotonate, attack this alkene, eliminate whatever the leaving group is here, and to install this right here.
The stereochemistry would probably have an impact. physical organic principles are such that I think you still want that leaving group trans on the ring. Gives you the best orbital overlap for the nucleophilic attack on the alkene.
Okay.
So you may want to control that coming in. The other thing to think about, I was trying to look at this. I don't think it would be a problem very much, but when you generate that enolate, it's actually an extended enolate. There are 2 double bonds in the enolate. And so if the hydroxyl then is a leaving group, you'd want to make sure you have selectivity at the alpha position. And you probably would. That's the much more nucleophilic carbon of the extended enolate. But you would want to go in and look at all the possibilities at all the different nucleophilic sites.
Yeah.
And just make sure you can avoid those side reactions in the control.
Yeah, that's a great point.
Yeah. Another thing I was looking at is you have this somewhat innocent looking hydrogen on that ring you're deprotonating, and the issue is that may crumble this, because you can epimerize that quite readily under base, because you can deprotonate at that CH at the bottom of the ring that is shown as the wedge here. And if that deprotonates, it can extend into an extended enolate within the 5-membered ring and just flop back and forth or freeze at the more stable stereocenter. It may not be a problem. It may be that the most activated proton for deprotonation is the one that you want, considering it's both next to a ketone and next to an alkene. But it's something to think about. You may or may not see epimerization of that proton.
Yeah. Yeah, that's an excellent point. That'll be something I don't really have thought of.
I was looking at your metathesis too, just because I love Andy Phillips' old metathesis chain reactions. If you haven't looked at those, I highly recommend them. Andy has done amazing stuff. You're going to react first, I think, at the monosubstituted alkene. And I was trying to see, with all these other alkenes there, where is their selectivity and where it's going to go? Since you're making an 8-membered ring, right? Mm-hmm. Normally, if you look at things like ring opening metathesis polymerization, they'll start with 8-membered rings because they will drive polymerization. So that's true. Uphill. Yeah, you know this because I know the Caro group.
Yeah, that's so true.
Polymerizations. So this is uphill. All the rest of your alkenes are tri-substituted, so they're not very reactive. I do worry about forcing this to go uphill to the 8-membered ring.
Yeah.
With the metathesis. You might be able to do it if you can drive off the ethylene. You yeah. I would look for some precedent there.
Yeah, that's a great point. Yeah. This wouldn't work.
Well, no.
I'm not saying that at all.
Yeah.
No. You want to go more reactive catalyst, or a catalyst that is really stable and can last a long time, so you can heat this in super dilute conditions for 5 weeks. I don't know.
No, I think metathesis is probably one of the top 5 most useful reactions ever, and it's definitely not 432 or 5. It's incredible. My issue with total synthesis and metathesis is often you wait a long time to try those reactions, and those because of the way the starting materials are built, they're not very diversifiable. You will get pretty deep before you realize the metathesis won't work. And that's where I try to I love metathesis. I think it's an amazing bit of chemistry. When it comes to making large rings and macrocycles, I really just stay away from it in proposing chemistry. It really makes me scared. However, this is olefin metathesis. You can try carbonyl olefin metathesis. There's actually a precedented one for an 8-membered ring just like this that I wanted to do first, and then I went away from it. Where if keep that vinyl group on the right side, the left side, alkene, you can make that a ketone. And that does a really nice carbonyl olefin metathesis, where it gives you the same product, but it starts with a ketone and a vinyl group instead of two vinyl groups.
Yeah. Is that the work with the guy at Ohio State? Oh my god, I forget his name. Nakib? Is that his work?
I I do not remember. Oh, it's Lay, the synthesis of huperzine Q. I have it here from Lay. They do a really nice carbonyl olefin metathesis. It makes a 5-membered ring, not an 8-membered ring. I'm sorry, but if you can make the transangular bond first, you might be fine.
Okay. Well, formation of 8-membered rings is, I would love some precedent on that. Some academic group out there wants to really help us out here.
This is what plagues a lot of those Ophiabolin syntheses, is the 8-membered ring. It just sucks. But that's why they're all like high-impact papers, because everyone has a creative strategy to make them.
Yeah. But with that, that was my forward synthesis, so I'll turn it over to Noah now. Really excited to see this full thing come together.
Yeah, let me second. Okay. Sharing now. Okay, we see the retrosynthesis slide?
Yep.
Okay, cool. So, the first thing we want to do is make this tertiary bromide. And so I kind of borrowed from some historical chemistry. This isn't something Seth invented, but having read all of his papers before joining the group, I thought this TMS cyclopentadiene unit is a really cool Diels-Alder substrate. It's more stable than cyclopentadiene. It's easier to work with, and it conducts Diels-Alder reactions quite nicely with endoselectivity. It's the only endo versus exo isomer you see. And you don't need a chiral catalyst for this. It's just what they use in the paper, but you just need, if you were to use a more substituted version, where these bonds here next to the ketones were alkylated or something, then that CBS catalyst might be more useful. I just copied the conditions. This is actually, with the cyclopentadiene without the TMS, it's a known structure. All of these are known. I referenced it down at the bottom, this Klunder paper from the Australian Journal of Chemistry. They're not the only people who've made this. This is just one that I liked because they end up doing they can make these asymmetric as well. But this is a meso compound. And so if you basically, I'm going to draw out the chemistry a little bit more, but you can take this and make it not meso by performing an epoxidation between the ketones, and then a Barton with extra base. You can do what's called a Poborsky rearrangement, and then you can attach this Barton ester to make this carboxylic acid derivative. From there, you can use the Barton chemistry to make a radical at this bridgehead, not this bridgehead, but this fused carbon, and trap with CBr4 as a bromine source. So going into it more, I'll spell it out. New slide. Okay. So the precedent for the Diels-Alder here, I just took it from Seth's paper. You can also, they do the exact same reaction with the exact same starting materials from an earlier precedent, but this is just one of many. Just for educational resources for other people. You can make pretty good EE on these reactions if you have a complex substrate. Looking at this asymmetric synthesis, you can, one of the intermediates, I think I have it down. No, I don't show it actually. But basically this is one of your intermediates, this 10 plus or minus 10 without the TMS, but otherwise it's the exact same thing. You can use pig liver esterase to actually selectively cleave one of these esters to the carboxylic acid. Now the ester itself comes from a Poborsky in ethanol instead of with NaOH, so you have to add a step to make the ester versus the direct carboxylic acid. And then this desymmetrization reaction is another step to make one of the enantiomers. But ultimately, there's an asymmetric synthesis element if you want to add 2 steps. Again, I probably would, because some of the chemistry later on might be useful to do that. But yeah, ultimately, this is the main fragment to start with, is this really nice protected enone type derivative. I'll pause here if anyone has any comments or questions.
It's already been published, so not much to say.
Yeah, well,
really cool.
That's what I like about this, is you can use that published chemistry to your advantage. The TMS group is not published, but it's a strategic incorporation of it. I think it'll still work.
Maybe tell us why that helps the fragmentation go at a lower temperature, and tell us a little bit of the physical organic chemistry there.
Oh gosh, I gotta look back into it. I imagine that the silo group helps stabilize the anion that the resultant alkene that comes from the retro Diels-Alder chemistry, but I totally forget. I know Seth's told me this too.
Just to guess, what is silicon known for stabilizing?
Anions and
What sort of anions and what sort of the other one?
usually oxyanions are pretty good.
Well, no, there's a specific effect that's known as the blank silicon effect.
Oh, is it it's the beta silicon effect?
Right. So in paracyclic reactions, anytime you can stabilize radical or cationic character, you're going to accelerate the paracyclic reaction.
Yeah. See, again, I don't look at this chemistry ever, and there's a couple of slides in here where I'm like, crap, I gotta go back to my initial knowledge here. But yes, no, I 100% bet that's what it is. Seth loves this protecting group because, I mean, it decreases the retro temperature penalty by about 300 Celsius.
It's a really nice idea.
Yeah.
Well, Seth's a really smart guy, and he has smart people working with him. So
I mean, I like working there. I can get on my soapbox about how great it is here, but I will move on. But you get some good ideas for sure. But from here, I abbreviate a lot of this. I'm going to go into every reaction. But this bromide is known to do halogen exchange with this copper lithiate source. It's a Gilman reagent. But
I think enone helps with that, right?
Sorry, repeat that.
The enone helps with that, with the anion generation, right?
Yes, helps stabilize that for sure. And so what's really nice about this is you can just make the lithiate, and it's stereoretentive, and so you could just trap with an electrophilic alkyl group. In our case, it'll just be methane. But this is another known reactions.
You would not get any 1,3 transposition there to the alpha position. It's not a true anion, right?
I think if you use other sources of the carbometallation, the initial carbometallation, you do get a little bit of alpha alkylation. But they said specifically the Gilman reagent in the precedent listed, I think in the Liu paper here, they generally get just the gamma position anion.
That's really nice.
Yeah, it's something I didn't expect until I just really dove into this. From here, this is where this TMS group is really useful. Not just the TMS, but this whole cyclopentadienyl fragment. I'll go into it, but basically you can add a Gilman reagent beta to this enone, and then I just say you can trap with Mander's reagent. That copper enolate's not going to be super nucleophilic, but you can split this up into 2 steps. I just figured I'd try it in one pot, see what happens. But this Mander's reagent's a great ester transfer reagent. And so from there, there's a known method for alpha alkynylation of stabilized enolates, sort of these 1,3 diketones. And so you can make that alkyne there. And what we'll see as I explain some of this is the facial selectivity is all dictated by this cyclopentadienyl block, basically. And it puts everything into a nice place. From there, you can chlorinate the alkyne. There's a number of ways to chlorinate alkynes, but silver is a great way to activate alkynes for deprotonation, just because that pi system on the silver or on the alkyne matches up nicely with the d orbitals. You get a nice like hard soft acid base type pair. And then NCS is electrophilic fluorine. Going into it some more. This is what I initially proposed. You can do this over 2 steps, it's fine. But the first conjugate addition is important because that is not an epimerizable stereocenter. You need to set it properly. And so what I've shown here on the right is just like a quick little optimized model where you can see the top face has this caged cyclopentadienyl group just looming over the alkene. And that's a feature of the Diels-Alder reaction. That's why it goes endo versus exo. Just this extra orbital overlap. But the copper itself, it's a pretty big reagent. You can just block the top face and add from the bottom. And that's how you get this first addition here with this hashed group. And then from there, again, copper enolates, not the best, but if we can swing it, it would be nice to just add the Mander's reagent in. and obtains a mixture of diastereomers, the ester transfer reaction. Again, you can just do this in 2 steps. You can just take the Gilman addition, quench it, and then deprotonate that and add in the Mander's reagent. That's also known. It's actually known, I think, on some of these types of groups with the cyclopentadienyl group. So that's that reaction.
Some extra Lewis acid, even if it's like some extra copper 2 in there to act as a Lewis acid, might work. Yeah,
absolutely. I think as much as I don't think step count is the main goal, it is nice to just purification wise to not run 2 separate columns. But yeah, no, I think there might be a way to swing it. If not, it's really not worth trying to make it one pot if you can just do it in 2 steps. But yeah, you'll see this facial selectivity argument with the TMS cyclopentadiene just comes back again and again and again. So looking at this again, the alkynation is interesting. I'll go through the mechanism a little bit, but it's the same thing where you make basically an enolate between the dicarbonyl species, and that enolate, it's blocked on the top face. Again, up here is this cyclopentadienyl group, and the bottom face, you can rotate this around. It's a lot more open. But it's a nice way to transfer an alkyne. Now, here's a mechanism. It's cited in this Wasser paper. But looking at the right-hand side, basically what happens is you can do a soft deprotonation, and a TBAF basically liberates this alkyne for actual transfer. But that oxygen of the enolate will add into this iodine. This iodine reagent's electrophilic. It's iodine 3. And then from there, you can basically transfer the alkyne to this carbene type intermediate, which is it's both positively and negatively charged, and so you can deprotonate the carbene to make the alkyne anion, and then that makes the alkyne. You can do this with ligands in there, but the issue with adding ligands to a very stereochemically complex reaction is they can either be additive and really help the reaction, and they can be matched in a sense, or they could be destructive and just kind of disrupt the innate selectivity that the molecule already provides, and then that's a mismatch. And so this reaction is known with both ligands and no ligands for 0% EE or 65% EE, but ultimately our substrate is rigged to give EE or DR as a function of this, again, this top blocking group, the cyclopentadienyl group. So that's kind of what I thought there. And yeah, before I move on, if anyone has any comments, I'd love to hear it.
I'm quite enjoying this ride right now. I gotta put together. This is a great presentation. I gotta put together some X-ray structures. That's a great for next time. I'm gonna do it next time.
You know, we love Spartan in this group. Spartan's getting really good at doing things really fast, including extremely accurate NMR calculations without the use of DFT. And so if your school or any school has access to Spartan Student, it's extremely powerful. Seth has done a really great job building a relationship between Yale and Spartan to make sure we get these resources. But the modeling is quite accurate. It's great. You can get energies and NMRs and stuff. So yeah.
Yeah. Moving forward, I'll start making 3D structures. I think it's really helpful for the viewer. But
yeah, don't need a model.
Anyway, chemistry is really cool though. I don't really have really cool. I have to check out particularly this alkynylation thing.
Yeah, it's neat.
The first step. It's really neat.
Yeah, I guess from here's one of the big things is this pos and con reaction. And there's like 8 million papers on pos and con reactions, but this one from Florida State University, Marie Kraft, was really nice, and I think it helped explain what I was trying to go for here. I will say I went to Florida State, so I love this reference. It's my favorite reference in the slide deck because of it, but also the chemistry is super enabling. Pos and con reactions are touchy. The conditions are tough. There's a bunch of metals you can use, a bunch of CO sources you can use, and you can get a mixture of diastereomers quite easily, and they're not always very separable. And this was a problem in the Reisman, ryanodine, ryanodol type syntheses as well that they figured out. But they're very sensitive to sterics. And so if you look at this reference here, what they show is that you get basically enrichment or selectivity for a specific diastereomer based on the stereocenter next to the alkyne. So you can see here I have basically ester group that is next to the alkyne. They have this OTBS group. But what they see is basically you get steric control to a specific face of the alkyne adding into the alkene. And so if the top face is blocked, the alkene is tilted, the methyl group on the alkene is tilted up, and that ultimately would give you a wedged methyl group from an otherwise unassumingly unselective type diastereomer mixture. And it's all just because the ester here, which you can bulk up, would block the top face and drive cobalt to the bottom of the molecule. I don't think this TMS cyclopentadienyl group plays ball here. I think it's pretty far away from where the reaction's happening, which is really nice because if it did play ball, we get the opposite DR, I think, potentially. So yeah, this is what I thought. I think this is a very challenging reaction, and we'd have to pull it off in practice. And kinetics are a big issue. Stability is a big issue, but the chlorine on the alkyne makes temperatures really low and makes these reactions happen quite fast. If you're interested, the Andy Evans at Queen's University in Canada just is, I think, one of the experts on this reaction, and they just released a really nice asymmetric ligand-controlled Pauson-Kahn reaction using chlorinated alkynes.
Glad you said that, because I haven't seen him talk about that.
He's awesome.
What do you think the effect is of you have the internal methylation on the alkene instead of having the hydrogen there in the model and in the precedent? So I'm pretty sure there are Pauson-Kahns that will make the quat center that has that internal methyl substitution.
Mm-hmm.
I'm just wondering, what sort of effect does that have on stereoselectivity and reactivity from what you saw?
You're talking about this methyl group here on the alkene right here?
Exactly. Yeah.
So I'm not sure how much it impacts things because I think a lot of methods lack sort of substitution of that alkene, mostly because they're not able to control the DR very well, and then they just get a mixture. I don't think it tempers the reactivity too much. I think sterically, the cobalt is still able to add across that bond. And this is where the Andy Evans work is really interesting because they intentionally put methyl groups at that exact position to get these reactions to go and show that they're asymmetric. So in terms of reactivity, I think it will react. In terms of sterics, I don't think it's that bad, but if you start bulking up that group past methyl, they do show that the EE drops quite a lot in their cases, and in my case, maybe the DR might drop. In terms of sort of the rationalization I bring at the bottom, where these examples have an H versus the methyl, I don't think as long as you have a cobalt species just sitting over that alkene, I don't think the methyl group will change the stereochemical outcome. I think the rest of the molecule is really what's more important because the methyl group's kind of planarized until it makes that bond. But I could be completely off base. I don't do these reactions.
Nope, I've only seen them discussed, but I thought it would be good for educational purposes to get your take on it.
Yeah, I mean, this stressed me out. This is like I was sitting here a couple days ago, like, oh my god, I got to redraw this. But if you rig the system exactly right, it seems like you can get it to do what you want. And the chlorinated alkynes are a really great way to increase your likelihood of getting reactivity in the first place. So definitely look at that chemistry from the Evans group. It was late last year. It's just awesome stuff. But what's also nice about it is you install a functional handle. That vinyl chloride is a very active cross-coupling partner because it's next to the ketone as well. So what you can do is they show this in the Evans group as well. They take those products and do cross-couplings. It's quite nice. I should have cited it. It's a really impressive reference. It was inspiring to see him talk about it in person. So you can take any, cross-coupling type nucleophile and combine that. So here I just showed PD in fragment C. Fragment C, you can buy this ketone. It's terpene derived. It probably smells nice. But it's known that you can do a selenium oxidation. I put bomb chloride. I meant to put TBS chloride. I was fussing around with my drawings before making these slides. But selenium and TBS chloride, that's known. This is a known intermediate in the middle. And then you can just do a CBS reduction, which I didn't want to take the time to figure out which chiral CBS catalyst would reduce this ketone to the right alcohol, but the spirit of the reaction is there, the strategy is there, which is you can take a known sort of non-chiral compound and make it chiral by using a stereoselective reduction. From there, you can do a
Let's figure it out real quick. So for the NIS reaction, is that stereoinvertive or stereoretentive?
I think it might be stereoinvertive. I gotta check, but there's other ways to do stereoinvertive halogenation chemistry. But the goal was to make it stereoinvertive.
Okay, so if it's stereoinvertive, you'd want the RCBS catalyst, I believe. Is that right? No, SCBS catalyst. Sorry. Yeah, you'd want the SCBS.
Yeah, I have to look back into it. It was just really late last night, and I was like, I think the spirit's here. But yeah,
this is the NIS. It's the NIS triphenylphosphine sort of Mitsunobu-like reaction. Is that what you're going for?
Yeah.
It's a PEL. Sorry, a PEL-like would be better.
Yeah, it's just an Appel.
Yeah. So that's invertive.
Yeah, and so you would want basically from the CBS reaction the methyl group to be a hash, and then just inverts to the wedge. From here, Noshel and Morgan have some really great strategies for using alkyl boranes, or in Noshel's case, the alkyl iodides. You can do a very fast lithium halogen exchange that retains the stereochemistry with T-butylene on secondary alkyl halides. And then you can trap that with this specific zinc reagent that I think just it stabilizes the zinc carbon bond, so it doesn't invert. And then from there, that's a Negishi partner. You can do a cross coupling with that, and they show that in this Noshel paper. Now, if you noticed, I drew fragment C as one olefin isomer, and then I draw it incorrectly in the top structure. Fragment C is the correct stereochemistry of the alkene. The top stereochemistry is just a typo, but the spirit of the reaction is the same, which is if you have everything defined in fragment C, you can just cross couple it in strategically.
That Noshel paper is, I originally had that, and then for some reason I didn't go with it, but that was extremely cool. Yeah, his stuff on cross coupling, awesome, as well as James Morgan's stuff. Honestly, we're going to do more future episodes like this, but honestly, I think like an SP3, SP2 cross coupling, we're going to come back to that a lot.
Yes, it's so hard.
They are stereoretentive.
These are so hard to do.
Yeah.
So it took me hours to find this reference. But yeah. From here, I want to point out some deception on my end, because if you come in with a racemate and add a defined stereocenter to it, you get a deracemization. You get a mixture of diastereomers, which is just a logical feature of synthesis. So obviously, we don't want that. That cuts your entire synthesis yield in half. And also, this is not the easiest separation to do because it's just kind of a pendant sort of stereocenter on a side chain. I don't know if silica would be the best way to separate these. So you get a mixture of diastereomers if you don't have the asymmetric starting material. So this is an opportunity late stage to enrich racemic material, but it has to be separable. And then the con along those lines is you get a mixture of diastereomers if they're inseparable, and you're just never going to resolve it. Your NMRs are going to look like trash, and you're never going to finish your synthesis. So, again, this is why I point out this solution down here. Just add 2 steps to your synthesis, obtain the enantiopure starting material, and that way you don't have to worry about this diastereomeric outcome. That's probably not separable in silica. But yeah. Going from there, we got this final angulation that I think can be guided by strain release. So this methyl ester, or whatever ester you want, you can hydrolyze that. It doesn't have to be lithium hydroxide. If it's a tert butyl ester, you can hydrolyze that with acid. There's a number of ways to do this. But from here, there's really nice decarboxylative cross-coupling chemistry directly from an alkyl carboxylic acid that you use iridium and nickel. I should have put a reference here, but there's a number of them where you can basically make an alkyl radical and then trap that with nickel and then cross-couple that with a sp2 cross-coupling electrophile. And so that's fragment D, which is down here. This is a known synthesis almost all the way through. where you take this symmetric alkyne and perform a hydrostanylation reaction that desymmetrizes this, and then you can protect one of the alcohols, and then you can basically burn off the tin and exchange it with iodine using I2. And so this intermediate here is now desymmetrized and protected. From there, again, I put mom chloride because I was fussing with my protecting groups, but it's TBS chloride. So TBS chloride can protect the other alcohol, and then potassium carbonate and methanol protects the acetate. And this is known fragment, which made me feel really gratified because this is not an easy fragment to make, and just again doing my retrosynthesis to disconnect to this way makes me feel like I'm on the right track. And then from here, they use NBS to brominate the alcohol. I didn't want the bromide because I was worried about cross-reactivity with an allylic bromide in a cross-coupling. So I figured that the allylic chloride would be deactivated enough to retain in favor and instead favor this vinyl iodide for cross-coupling. So yeah, that's fragment D, and that's how we couple those in there. I think nickel's really nice here because you don't have too many other functional groups that are going to mess with it. You might get some sort of, when you decarboxylate up here, this alkyl radical can certainly shuttle through this unsaturated ketone. But at the end of the day, this is the most sterically accessible position for cross-coupling. It's the least hindered. There's fewer groups around it, I think, compared to the methyl and this other alkyl group. So you might be just fine, I think, getting a regioselective decarboxylative cross-coupling. But again, we have to try it and see.
Not often you hear where you're forming a quat center being the least hindered possibility.
Yeah, I think this cyclopentadienyl group can still hover over there for sure. But in terms of bringing the radical through the system, there's other steric complications as well. And it's one of those things where I just really wanted to see where it would go. And if it's a problem, there's other kinds of chemistry that you can engage in, like alpha vinylation.
I think the bigger question is whether you can get anything there at all.
Yes.
Not necessarily where will it go.
So this is where the TMS cyclopentadiene is really great, because you can just remove it. You can just clip it off and continue the rest of your synthesis as such. And what that does for you is it removes some of the steric encumbrance of this group of the carboxylic acid by performing a retro 2+2 back to this unsaturated ketone. So I think you might be able to mess with the sterics a little bit to get something in there.
Yeah. I think if you did that, you'd have a much better shot.
I think so too. But I really like this group. I just think it
you don't want to let it go.
I don't want to let it go. I think it does its job quite nicely, but I agree. The next thing is you can perform
with that.
Go.
Just one more thing. With the decarbonylative or decarboxylative cross coupling, that has been shown to make vinyl quat centers before, or is this a new proposal?
I honestly didn't look into it too much. I don't know about vinyl quat centers, but it has been shown to make vinyl to conduct reactions with vinyl halides, especially vinyl iodides. And so I need to look back into the precedent. It's a good point. Again, I don't make quat centers ever, so it's not something I think of. So it's a good question.
Secondary centers are 10 times harder than primary. Quaternary centers are 100 times to 1,000 times more difficult than secondary centers in many cases.
And is that just a steric issue?
Yeah. And it's not just the sterics of making the carbon-carbon bond. It's the sterics of getting all the reagents in there also to make that bond. So there's just, with any other lesser substituted carbon, there's always a hydrogen that the reagent can be nearby. But with quat center, there's no corner, there's no mercy, there's no allowance. So
sure,
it's much more difficult to do it.
That's interesting. And yeah, I kind of wonder if one of the main byproducts out of this would just be, say you can metallate with the nickel, you might just get beta hydride elimination. Because the rest of the reaction might just not be accessible.
Yeah. That's hard to do with nickel.
Yeah.
But
no, that's an interesting point. I really didn't think about that, and that might make this quite challenging if we can't get it to work. That being said, you could also try to make the enolate and do enolate oxidation type chemistry or enolate couplings. But again, at the end of the day, you're making a quat center through cross coupling. So it's tough. I see your point.
GG's.
Yeah. But assuming that reaction can work, and maybe this is a feature for chemical design and methodology development, there's a lot of chemistry known with, I think Bruce Lipschitz does a really great Negishi cross-coupling type manifold, but often his chemistry relies on water exchange of zinc and halides at really fast rates. So if you look at his work, and this isn't a Lipschitz type disconnection by any means, but it inspired me to think about rapid, mild metal halogen exchanges of allylic halides, which in this case, zinc with some of his surfactants, they do that. You can basically exchange chlorine for zinc, which can transmetallate to other things, or you can try magnesium, you could try terpetolithium, but the idea is you can do a allylic, mediated metal halogen exchange, and then that metal could either directly perform a cyclization reaction to make the last quat center, or you can try to add palladium into there and do some sort of conjugate addition type chemistry, or you can potentially make this into a radical substrate that could do a Giza coupling into the beta position of this enone. There's a lot of options. The chlorine's really just a placeholder for a reactive handle. You can even use a carboxylic acid and do a decarboxylative Giza coupling at the beta position. So there's a lot of options. But what I like about this is with this last the second to last stereocenter set by this decarboxylative cross coupling, you can only get one facial addition to this enone. Only the top face is going to be accessible because this other wedged alkyl or vinyl group, it can't go to the back face of the molecule. So you're really using the innate facial selectivity of the molecule to control the last stereocenter. And then I thought, if it's an anionic reaction, we can try our best to trap it with either like a triflate or a tosylate. That's another palladium type reactive element to deoxygenate and make the last alkene. But yeah, I don't know. I think this is a very tricky step. So if anyone has comments on the cyclization, please let me know.
I agree it's tricky, but I think you brought out most of the salient points on it.
Do you have to worry about, do you have to worry about elimination at all? I actually don't even know, as long as the alcohol is like protected, do you have to worry about elimination at all of the, I guess the alcohol, well, protected alcohol, I guess. I don't know.
I think the alcohol is fine, but the chlorine might not be, right? The chlorine, you can easily do an extended E2 type elimination of the chlorine. But it should be pretty stable, I think, just because it's not an iodine. It's not a great leaving group, to be honest. But yeah.
It's a leaving group, though.
It is a leaving group.
That's a problem.
Yeah.
I don't know. I just always worry about allylic halides anywhere you have a transition metal. But
yeah.
Maybe that's
one thing you can do is you can make an allylic acetate, so you can keep the acetate from down here, and you can engage in Suzy-Trost type chemistry. So you can make if this chlorine was an acetate, you can make a palladium allyl pretty mildly, and that might favor the 5-membered ring formation over like a 3-membered ring formation. So it's almost like a Suzy-Trost heck type addition to this enone, which may be a bit more favorable. But there's options, is I guess what I'm trying to say. And then, eventually I'd like to arrive at this vinyl oxy type substituent, whether that's a tosylate or a triflate, because there's a lot of known chemistry on, as long as you can do an oxidative addition, it's feasible that you can burn off your leaving group with a H, with a proton source. And so I put the tosylate here, but triflate chemistry is more known. It's just the triflation reagents are kind of spicier. So it's nice to have a vinyl tosylate here in a one-pot cascade. But you can do oxidative addition across these and treat them with like isopropanol and burn that off. And then from there, all you got to do is TBAF and heat. So you take off your TBS groups with TBAF and then you heat this to do a retrocyclization to get bipolarolide.
That's yeah. Do you have to worry with palladium? And I guess, I mean, how selective do you think the deoxygenation would be? I mean, I don't know. Is there anything really kind of around?
It should be pretty selective because the deoxygenation requires oxidative addition. It's not a palladium hydride like palladium on carbon. It's basically you perform an oxidative addition between this carbon-oxygen bond, and then isopropanol donates a proton basically to burn off the palladium complex. Yeah. And if you can't do oxidative addition, you cannot hydrogenate the species. That's why this chemistry is really nice.
Yeah. I'm sure there's plenty of deoxygenation strategies maybe you could try.
Yeah.
At this point. Yeah. It's really cool.
It's problematic.
Yeah.
I will say it's a problematic synthesis, but this is like, if we're talking about a podcast on how to approach molecules, this was what came to me, and I think this is how I think. So
yeah. Thank you for sharing. Yeah, I mean, like I said at the beginning, this is a open discussion. Try to work through this, not a you're wrong.
Sure, yeah.
Although sometimes you might be, but no. Yeah.
I'm okay with being wrong.
Yeah, please. I mean, yeah, we want to. One of the purposes of this is to engage the chemistry community. We want to be able to, if you've experienced one of these types of problems, let us know. We want to build the strategic bank, I guess, or strategy bank. Here.
Sure.
Jeremy, any final thoughts from you about maybe the molecule in general, or maybe strategy you would approach when looking at this, or any final comments?
I'm looking forward to seeing how someone eventually makes it.
Yeah, right. If there's a natural product synthesis of this compound, we have to be cited as one of the key references.
Oh, I'm sure.
Right? Yeah, right. This will be the first reference that is cited on that paper.
Only if they use one of your routes.
Yeah.
Well, if they use one of my routes, we might be talking more than a reference.
Yeah, right.
But no, if you guys are interested, you should read the recent synthesis of Bipolarolide D in Angew, because their approach to this type of scaffold is quite interesting, and it goes through it builds a lot of complexity through an extended Prinz type cyclization. So check that out.
Yeah. Well, with that, we're going to conclude here. That was our first episode of How Would We Make This? And so that was how would we make Bipolarolide D. I want to thank Noah for being an excellent co-star on this, and your time in total synthesis. Working graduate students, grad school life is crazy, but we're doing this for fun. Jeremy, thank you for your time as well and your insight on this. It was excellent having you both back on the podcast, by the way. So make sure you check out those individual episodes. And if, like I mentioned before, if you want to get involved, make sure you're following us, everyone on Twitter or X. Make sure you're following the Synthesis Workshop. If you have suggestions for a natural product target for us to try, send it to me. Send it my way. I'll be sure to give it a shot. And hopefully, we can do this, once every 2 months. I think that's a good turnaround time. Well, maybe not Jeremy and Noah, but if they want to come back on, they're more than welcome to. But at least for myself, hopefully we can get this going every 2 months. So, but with that, I'd like to thank everyone again, and we'll see you soon. So, Jeremy, Noah, thank you.
Thank you.
We'll see you guys.
See you.
Of course.
Alrighty.